Welcome to Part 3 of the Framework Examples module. In earlier parts of this module, we've described scope, commonality, and variability analysis and illustrated how you can apply it to ACE and Android. We've also spent some time covering some of the framework components that you find most commonly used in Android applications. Now, we're going to spend some time in this part of the module talking about some of the frameworks you find in ACE. The topics we'll be discussing are described in C++ Network Programming Volume 2 book, which describes frameworks in ACE. We'll also be providing links to earlier papers that talk about some of these various concepts. And of course, we'll be emphasizing commonality and variability throughout this discussion as well. Let's first start by talking about the Reactor framework. It's one of the core frameworks that you use very commonly in ACE. If you take a look at the way many operating systems handle event multiplexing and event handler demultiplexing, they often use mechanisms like select or poll that support something known as initiation events and support them synchronously. The basic idea here is that if you want to be able to read or accept or write to a socket or a file without worrying about blocking, you have to use these event multiplexers like select to ask permission. And when it's OK to initiate such an event, that demultiplexer returns, and you'll be able to go ahead and do your thing without worrying about blocking. So what the Reactor does is it takes those basic mechanisms and it provides a framework that automates many of the tedious and error-prone aspects of handling and dispatching and demultiplexing and so on, the various initiation events you'll find in common operating system environments. So what you typically do with a Reactor is you define a number of different event handlers, you subclass from some base classes that ACE provides, and then you register those handlers with the Reactor, and you tell it what kinds of events you're interested in. Are you interested in reading events, accept events, connection events, writing events, timer events, signal handlers, and so on and so forth. And then the Reactor is responsible for keeping track of all those different types of events and calling your handlers back when they occur. If you take a look at the link here, you'll see that there's a paper that describes how to use the Reactor. It's also described in the book, of course. From the point of view of commonality and variability analysis, you can think about the ACE Reactor framework providing a common interface for various kinds of signal handling, I/O events, timers, and so on that are used in a synchronous initiation event-driven model. The variabilities naturally will be the kinds of event multiplexers that you're working with. Are you working with select? Are you working with poll? And so on and so forth. And there's also variations in terms of how the dispatching gets done. Are things dispatched in priority order? Are they dispatched in first come, first serve order? And so on and so forth. So the Reactor gives you a nice environment for being able to leave those responsibilities to the framework infrastructure so you can focus on the behaviors of your application or service components that you define by extending the framework. Well, it also turns out that in addition to initiation events provided by many operating systems, some operating systems also provide support for so-called asynchronous processing and completion events. For example, Windows supports something called I/O completion ports and overlapped I/O, which can be used to initiate operations and then learn later about the success or failure of those operations when they complete. So this is typically something that can be provided by a framework in ACE called the Reactor framework. The Reactor framework is responsible for allowing applications to invoke these operations asynchronously, and then it keeps track of their completion as they run asynchronously, and then dispatches completion handlers when the operations have concluded. If the operations fail, of course, you just need to know that they failed, perhaps with the reason why. If they succeed, the Reactor framework can pass back to you things like open connections or data that was read asynchronously or buffers that have been written successfully asynchronously, and so on and so forth. There's a link here that describes the Reactor both as a pattern as well as a framework. From the point of view of commonality and variability, the Reactor, like the Reactor, provides a common interface for handling different kinds of asynchronous timers and I/O operations and I/O events. And it works not only on platforms like Windows that have good baked-in support for these capabilities, as well as on operating systems like different versions of Unix, where they support some forms of asynchronous I/O through the AIO operations, AIO wait, AIO suspend, AIO read, AIO write, etc. And so the Reactor framework in ACE encapsulates these diversities and provides a common interface. Naturally, the variabilities are the way in which things work in different ways in the implementations. The Windows way of dealing with asynchronous operations is wildly different from the way that Unix does it. And so those variabilities are encapsulated in the framework behind a common interface, thereby making it easier to write these kinds of applications that might run effectively in a portable environment or a diverse environment. The next framework we're going to talk about is the Acceptor connector framework. Traditionally, when people have developed networked applications, there has been a tendency to tightly couple a couple of things: the service handling initialization code, the connection management code, and ultimately the application processing that takes place once services are connected and initialized. The Acceptor connector framework automates connection setup and service handler initialization. So those parts of the steps are handled for you by the infrastructure rather than having to be rewritten from scratch again for every application developer who's trying to write a networked application. The basic idea here is you have an acceptor, which is the passive side that waits for something to happen. There's a connector, which is the active side that goes ahead and initiates the connection either actively or passively, or sorry, either synchronously or asynchronously. And once things are connected and established, then the acceptor and connector initialize service handlers that actually carry out the application level protocol and communication and conversation between the connected parties. There's a paper at my website that talks about this. It's also, of course, covered in much greater detail in the book. From the point of view of commonality and variability analysis, the Acceptor connector framework provides a common interface for synchronous and asynchronous, active and passive connection setup and service handler initialization. Many things are done in a common way, much less tedious and error-prone than trying to program these things in the low-level form. Some of the variabilities it supports include different communication protocols that can be plugged in through various types of template programming mechanisms. You can have different types of service handlers that can also be plugged in as templates using strategy patterns and policy-based design. And it also has various ways of being able to factor out the logic for creating service handlers, accepting and connecting the service handlers so that they're connected to their peers, and finally activating those service handlers to run in various event handling and/or concurrency models. So a lot of this stuff is now taken out of your responsibility, you as an application developer, put into the framework, and so your code becomes much smaller, much cleaner, much more portable. The next framework that we'll talk about is something that's called the Service Configurator framework. And it's responsible for static and dynamic configuration of service components. Traditionally, when people built applications, and especially networked applications, there was a tendency to link everything together statically at static link time. But that's very inflexible. You often don't know until your program is in the environment it's going to run some of the characteristics you might need to know to optimize it properly. You might not know, for example, at design or compile time, how many cores you're going to be running on, or what the load of the machine is on, or what kinds of versions of the operating systems you're working with. So if you can defer some of those choices, you can use the Service Configurator framework in order to be able to script the way in which your application is configured, the way in which the services are brought together and initialized. And basically what happens is that the framework reads a script, you can pass it in as a string or as a file, and it takes a look at a set of directives in that file that tell it to do things like dynamically link in a particular dynamic link library or shared library, extract factory functions from that library, invoke them to create the appropriate services, and then if those are properly initialized, to store them in a service repository so they can be used throughout the lifetime of the rest of the application or middleware infrastructure. This paper describes the ACE Service Configurator framework both as a pattern and as a framework. It's also covered in the book, of course. From the point of view of commonality and variability analysis, the Service Configurator framework provides a common interface for controlling service life cycles. In other words, when they're created, how they run, how long they run, how they're shut down. And it also provides a common scripting language for interpreting these service directives that tell it how to perform its tasks and behaviors at various late binding phases of the system and application lifecycle. The variabilities it supports, well, you can configure many, many different kinds of services at different points in time. A server could have many services that are brought in later in the design cycle, even while it's running. You can change the service implementations very easily. And you can also, of course, encapsulate various kinds of underlying operating system linking and unlinking implementation mechanisms for loading and unloading these DLLs and shared libraries in and out of your address space to give you just exactly what you need and no more when you need it. The next framework we'll talk about in ACE is something called the task framework, which provides active objects for queuing and processing messages concurrently. You've undoubtedly all programmed passive objects for many years. A passive object is just a regular C++ or Java or C# object that, when called, borrows the thread of the caller to do its work. Active objects, as we'll see in a moment, are a little bit more lively. What they typically do is they have one or more threads running inside them, and when someone gives them some work to do, if that work is not done immediately, it's stuck onto a thread-safe message queue internal to the task, and then at some point the background threads can pull messages off that queue, perform the processing, and then do something else with the messages. We'll talk in a moment about some of the things you can do with those messages. This particular framework in ACE is described in the paper at the bottom here. From a commonality and variability point of view, it provides a common interface for queuing and processing of messages concurrently within a single address space. That's the unit in which a task works. And of course, it provides support for various variabilities as well. Different concurrency strategies, different synchronization strategies, different memory management strategies for the memory that's used to allocate where the messages go in the queue that's stored internally to the task, and so on and so forth. The last framework we'll talk about is something called streams, and it builds on some of the things we've already discussed. In particular, it builds on the task framework. And what it allows you to be able to do is compose and process layered services. In earlier parts of this course, we've talked about monolithic versus layered and modular service composition. Well, the streams framework in ACE gives you a nice way to handle those kinds of design dimensions without having to do all the work yourself. What you basically do with the streams framework is you take a group of tasks and you can combine them together into a pipes and filters or pipeline-like architecture. And data can flow between these tasks, which can either process the data immediately or can queue it for later processing within a thread or threads that are running inside the task. So you can basically think of this stream as being a pipeline of tasks. There's a paper here that describes how this works. From a commonality and variability point of view, it provides a common interface for doing layered service composition and message passing between tasks. From a variability point of view, you can have many different numbers of layers. You can have different implementations. You can pass different kinds of messages. You can compose the services in different orders. And of course, you can also implement different kinds of layered concurrency architectures, things like task-based concurrency architecture or message-based concurrency architecture, which is another concept that we discussed earlier in the course. So to summarize this part of the module, ACE provides a number of frameworks that support inversion of control, and it also embodies many commonalities and variabilities that you'll find when you develop concurrent and network software, application software, system infrastructure software, and so on and so forth. These frameworks that ACE has are based on a pattern language, which is largely documented in the Pattern-Oriented Software Architecture Volume 2 book, with some help from some other patterns from other sources. And we use this pattern language throughout the development and application of ACE for a number of purposes. One important purpose is to preserve crucial design information and design intent that applications and middleware frameworks leverage so that people who maintain these frameworks and use them have a much better idea of how to apply them successfully. to avoid some of the common traps and pitfalls that might otherwise arise. It also, of course, facilitates the reuse of proven design techniques. For example, the streams framework that we were talking about was inspired by some of the patterns and ideas that were in the System 5 Streams Communication Protocol stack framework that Dennis Ritchie and others developed at Bell Labs many, many years ago. Another nice thing about using patterns in the context of frameworks in ACE is they help guide design choices for application developers. Once the developers understand the wealth of the different design dimensions available to them, as we've talked about in previous parts of this course, then they can start to pick and choose the appropriate frameworks to be able to get the kind of behavior they want in the operating environment or the application domain in which they're trying to build their software.